let's go ahead and let us do our thing, okay, man? Sorry, that's one of our really close friends, distracting one of the Gen Chem 1 students that are trying to learn. I'm sorry, Sammy.
I have no clue what you're talking about.
Okay, so the last thing we left off on Wednesday was this question about these quantum numbers violate one of the following principles of quantum mechanics, I guess. And the question is, which principle does this violate? And what do we notice about these two quantum numbers right here?
Yeah, they're the same.
They're the exact same, which says that these two electrons are occupying the same what?
Same,
Same exact position, right? You can say position, same exact orientation in space. And what principle state no two electrons can have the same quantum number? Pauli's exclusion principle. So yeah. All right, what now? So Hund's rule. Anyone want to tell me what Hund's rule is?
yeah, you have to fill it up one at a time before you double up.
Right, so we know that we have our 2p subshell has 3 orbitals in it, right? When we do the n equals 2, L is equal to 1 for the p, and then our m sub L can be -1 or 0 or +1. So each of these corresponds to a single orbital, and that's why we have 3 total orbitals. So our 2p subshell has 3 orbitals, 1, 2, 3, right? Now, when you're filling up the 2p subshell, Hund's rule states that when you add an electron, it goes into an empty orbital, and then if you add a second electron, it goes into the next empty orbital. So if we add it up, they both start up, and then if we're going to add a second one, we don't do this. We're not going to add it to that one that already has an electron. Why? Because we know electrons have repulsive forces against each other because like charges repel, right? So it doesn't make sense. It would be very energy costly to add an electron into an orbital that already contains an electron when you can just add it into its own empty orbital, right? So you get less repulsive forces. And so we're going to add a third one. Where is it going to go? Third orbital, right? Now, once we fill up those 3, this is when we start doubling up. So the next electron would go into the first orbital, but it would have the opposite spin, right? Because if it had an up spin as well, then they would have the exact same quantum number. So it would have a down spin. And then add another one, and then add another one. So that's what Hund's rule states. It states that if you add an electron to an orbital, it's going to go into the next empty orbital before it starts doubling up with the other electrons. So what about the Aufbau principle?
Energy levels first.
Exactly. So we fill electron subshells starting from the lowest energy to a higher energy level. So we always start with our 1s, and then we go to our 2s, then we go to our 2p, then we go to 3s, then we go to what's next? 3p, and then we go to what? 4s, and then we jump down to 3d, and then it would be 4p. So I wouldn't write this down just because you can infer this by looking at the periodic table. But it's essentially the order that the subshells are filled up. And that's Aufbau's principle. And then the Telecali effect is meaningless. So
I mean, it's not meaning.
it's pretty like,
It's not even spelled correctly.
yeah, for real. You know what?
Work in progress.
Yeah. So it's nothing. It means nothing. Absolutely has no point. And if you see this on an exam, make sure you like just cross it all the way out like this. Okay, like make sure you do this because it basically doesn't exist. Yeah.
What doesn't exist?
Well, the thing that doesn't exist. I mean,
So how can it exist?
and then
Let's just say being number 2 is a Telecalipali effect.
Why are you dragging yourself?
Okay, and then E is just something that we decided to add like a whole paragraph to see if anyone wants to choose that. I hope you wouldn't. Okay, so does it make sense why Pauli's exclusion principle is the right answer? Because that principle states no two electrons can have the same quantum number, because if they did, they would be occupying the same exact space. All right, and that's what's seen here, right? We have exactly same energy level, same subshell, same orbital, and then same spin, right? Now, what about this one, number 7? I'll give you all 30 seconds to write something here. Be done by now, I would assume. So for an electron in the 5p subshell, what must the n value be? 5. For an electron in the 5p subshell, what must the n value, the energy level be? So an energy level is the n, right? That's their n quantum number, because we have 4 quantum numbers, or technically all of these 4 make up 1 quantum number. So n, l, m sub l, and then m sub s. So we're asking about the energy level, which is n, right? And obviously, the 5p subshell must be on the 5th energy level, right? So n must be equal to 5. All right, and then what must the L value be?
Anything between 1 to 4.
Okay, 0. So I hear a lot of,
Oh, yeah,
Isn't it-
1.
Isn't it 1 because
0 or 1, yeah.
it's 1 because why?
it's P, because it goes 0, 1, 2, 3.
Yeah, so P, so when we have an L value,
It's just 1.
when L value is equal to 0, this corresponds to an S orbital. And then when L value is equal to 1, this corresponds to a P orbital.
I know that,
And then when L value is equal to 2,
LS.
it corresponds to D.
um,
And it's so on. So the L value of 3 would be an F orbital, and then it would keep going up from
Say
there.
memorize it up.
So if we're talking about a 5,
Maybe memorize D.
subshell,
D's like a flower.
what must the L
D is
value
like a
be?
dumbbell thing, and the S is like the spirit.
1, right?
Can you repeat that? Sorry, it was kind of muffled.
So, so in order, it's asking for an electron in the 5p subshell. So do we all agree that the n value, the quantum number here must be 5 because it's in the 5p subshell, which is on the 5th energy level? Do we agree on that?
Yes.
Okay, what about the people on Zoom that asked the question?
Yes.
Perfect, okay. Now for an L value, now the next thing is to assign the L value. So we know that when L is equal to 0, this corresponds to the S subshell. When L is equal to 1, this corresponds to the P subshell. And when L is equal to 2, this corresponds to the D subshell, right? So if it's asking for the 5p subshell, what must our L value be? To the person on Zoom.
Oh, 1.
1, right? Because when L is equal to 1, this is talking about the 5p subshell, or not the 5p, it's talking about the P subshell, right?
Right.
Okay, perfect. So what can our M sub L value be when L is equal to 1? So it can be -1, or I'm making sure I'm gonna put or in there for each part, so that way you know it's not all 3. It can be -1 or 0 or +1, right? So it can be any of these 3 right here. It can't be all 3. So when we talk about a single electron, we're talking about only one space. So it could, if you wanted to write all the possible combinations, we have M sub L, M sub L, M sub L equal, and it would be -1, 0, 1.
I have a
Quick
question.
Yeah.
Oh,
I was just gonna ask, like, does it matter which one you put? Like, if you were to put -1, 0, or 1 for the question?
It doesn't matter, it's -1, 0.
Yeah, it wouldn't really matter if it's -1, 0, or 1, because it just asks for one, like, an electron, like a possible electron in the orbital.
Yeah, so say if this was a multiple choice question. You would just be looking for something that says, basically says n equals 5, L is equal to 1, and then a valid M sub L number, which we know has to be between -1 and 1. And then your magnetic spin quantum number would have to be, you really only have two options, so it could be +1/2 or -1/2. So to answer this, move this over here. If you had written anything like an M sub S of +1/2 or -1/2. If you had wrote in n equals 5, L is equal to 1, M sub L is one of these three, and then M sub S is one of these two, you would have got the answer right. Because all of these orbitals are on the 5p subshell. Would I just be, would L just be equal to, like, what is it?
It would,
It's a p orbital, so it has to be.
so basically, like, can L be 1 or can be one?
Right, just like in
Okay.
class today, he was talking about it was n-1, or is that something
No, it
totally
can't.
different?
L can be 0 to n-1.
Like, that's like the maximum, like, range of values.
Right.
But this question specifically asks about the 5p subshell. Since it only talks about p, the only value can be is 1.
So if I just had n equals 5, then L could be any of those, but
Exactly.
this one specifically is
Yeah, L
denoting that one.
N equals 5, L can be 0, 1, 2, 3, or 4.
Right.
Yes, but it's asking about the P. So,
So this one is like a very specific location, and we're asking that not what any n5s could be.
exactly, yeah. Oh, yes, yeah, exactly, Michelle. The subshell makes it specific. It's talking about the 5p subshell. So we know that the p orbitals only occur in a quantum number that has an L value of 1. If you put in an L value of 2, you wouldn't be talking about a p orbital anymore. You would be talking about a d orbital electron.
And
Okay,
that's just, you just have to memorize those, right?
yes. Okay. So any questions on that? I know it's a very confusing topic.
I have a question. How did you get the M sub S, the +1/2 or the -1/2?
Yeah, so that M sub S values can only, because each orbital can only contain 2 electrons, M sub S can only be +1/2 or -1/2 to denote that each electron can either have an upspin or a downspin in that orbital.
So will it always be +1/2 -1/2?
It'll always be +1/2 or -1/2 for a single electron,
No matter what the subshell is.
no matter what the subshell is, correct?
Got it. Thank you.
Good question, thank you. Okay, perfect. Keep asking questions. This is the time to iron out any misunderstandings here, okay? You got number 1 and 2 in the house to help. Yeah. I'm just kidding, Rich. Okay.
That's cool. On number 1, no cut now, so it's fine.
Yeah, because I'm not in this class. All right, you can do number 8.
Okay, so number 8S, which of the following sets of quantum numbers is invalid? Give you all about, say, a minute and a half, so it's problem.
Her mom can you fix her? Not very well.
She's exposed to all.
Oh, what? It's not good.
Oh.
Yeah, no, sure. It's not COVID, trust me.
No, she's sick.
She's
But
just
not
sick.
that type of sick.
Yeah, no, that's a mistake. I never lie.
Do you want to take a picture?
Oh, sorry. Get clinical hours.
She's so cute. My poor baby.
That's so funny. I mean, it's not funny, actually.
Yeah, it's really not.
Okay.
30 seconds. Speaking of 30 seconds, Dylan and I will be teaching y'all classes next week, Thursday and Friday. Except I won't be going Thursday because I have an exam.
Oh, go look at your exam.
It'll just be.
Oh,
Tomer, I know he's
Tomer.
in Austin. Hi, Tomer.
The time looking like Rich.
Time's up. Right, what did y'all get? Is there anything?
E.
Yeah, it's E.
All right, I hear some E's, I hear some D's. Let's see which one it is. So, E, okay, so what's the question? Which of the following sets of quantum numbers is invalid? Let's look at the first one. N equals 2, right? Is that valid number for N?
Valid.
Why? Like what?
It's an integer.
Yeah.
Between 1 and infinity.
Yeah, so it's a positive integer between 1 and infinity. So N was good for this. What about L? Is that valid?
Yeah.
Which orbital would that correspond to?
The S orbital.
Yeah, because it has a 0, so 0 corresponds to the S. So yeah, that's also valid. What about M sub L?
Yeah, it's valid.
Yeah, if L is 0, the only other value M sub L can be is 0, because it's negative L to L, and negative 0 and positive 0 doesn't exist, it's just 0. So that's also good. What about M sub S?
It's valid.
See, yeah, M sub S can either be negative 1/2 or positive 1/2, no in between. So yeah, that is correct as well. That's all good. What about B? N is equal to 4.
That works.
That is good. It is a positive integer. N equals 4. What about L? L equals 2.
Yeah, that works.
What subshell would that correspond to?
D.
Yeah, so this is a 4D electron. What about M sub L? Is that good? Yeah, because it's from negative L to positive L. So it could be -2, -1, 0, 1, 2. And then, yeah, you can see here 1 is a possible option. So M sub L is good. What about M sub S? Yeah, that's fine. It can either be -1/2, positive 1/2. All right, what about C? N is good because it's from 1 to infinity. L is good. What subshell would that correspond to? 5p, yeah, but it's a 1. What about M sub L? Is that good? Yes, -1. What about M sub S? Also fine, right? Because it's 1/2 to -1/2. That's all good. Now here's D. L is what, or sorry, not L. N is what? 1.
Yeah.
That's good, right? Because it can be anything from 1 to infinity. L is 0. So what shell does that correspond to?
S.
Yeah, because L can only be n-1, and then L, the maximum range for L is equal to n-1, so 1 minus 1 in this case. 1 minus 1 is just 0. And then M sub L, right, as we said in A, the only value can be 0 because it's from negative L to positive L. So that's all good there. And then M sub S is equal to positive 1/2, so you're good. The only other answer is E, but let's check. N is equal to 5. That's good, right? Valid. What about L?
It's valid.
And it is in fact the F subshell, so that is good. What about M sub L? Is that
Not
valid?
valid.
Not valid.
Why not?
Because the L is only 3.
Is that why?
Right.
Yeah.
So that range.
-3. You can write out your possible combinations. M sub L is equal to -3, -2, -1, 0, 1, 2, 3. So there's only these possible combinations of what M sub L could be. But in this case, M sub L is -4, so that's not valid. And M sub S, of course, is 1/2 and -1/2. All right, real quick, let me give you all a set of quantum numbers. You tell me if they're valid. or not. So we'll say N equals 3, L equals 2, M sub L -1, M sub S equals
Okay,
5/16.
so I'm writing a whole sheet paper. So what if it asked how many electrons are in the subshell?
If it asks how many
Or
electrons,
not in the subshell, in an energy level.
so if
Same
that-
equation.
Use the two.
2n squared equation.
What if L or F, wait, what is the L of F subshell? 3?
Yeah, it is 3. So back to these sets of quantum numbers. So let's say your n is 3, your L is 2, your m sub L is -1, your m sub S is 5/16. Is that valid?
No.
Why not?
That's to be 1/2 or -1/2.
Exactly.
What
What
if-
two
What
values?
if it was 8/16?
Then you're being
Yes.
ornery, but it's still.
Interesting.
Yeah, it has to be 0.5, positive, -0.5 or positive 0.5.
Yeah,
So just anything that's 1/2.
So 8/16.
it works.
It's
Still 1/2.
So it's okay.
Yeah.
I don't think y'all would see that on the test. Sorry, I was just like,
It either. But it is-
that'd be a trick question. Okay, keep going. Oh, what, you want to do this one? Or yeah?
I can't. That's exactly what I thought. Okay. In general, a human eye cannot detect photons of frequency greater than 750 terahertz. Find the maximum energy of a photon that can still simulate the receptor. And what is the name of this receptor? I'll give you all about, it's more on the difficult end, let's say 2 minutes.
That- Actually, Wednesday was TA.
I know,
Application.
you sent your little,
Yeah, no one gave us credit cards or anything.
really,
Oh, sorry about that. I would have sucked.
We have to take social security number.
oh, that's good next time.
Well, we also take cars, payment.
Yeah,
Audis that have dents in them because of people hitting bikes.
bikers hitting them, yeah.
Sandra, you are the best for that. Look at that. She's one.
Gee.
Wow.
It's not actually.
Well, actually,
I mean, technically it is, but like
Like
it's.
when I was reading, it said that there's not like a functional use for it though. Is there?
well, because we have elements in the 7th energy
What is
level,
television?
which have an L value up to 6.
I don't know what it is.
So I guess those can be used, but like the application of.
I have a question.
Oh,
Yes. What's up?
So for the quantum numbers, does n give you L and then does L give you M sub L? Is that like how that works?
So N, I wouldn't say gives you L. So N, we know it can be any integer from 1 to infinity, right?
Right.
But we know that L can only go from 0 to N minus 1. So I guess kind of it can tell you all the possible values of L, but it can be any of those. So if you had an N of 100, which we don't see, but this is just an example, right? So if you have an N of 100, you can have a L value of 0 to 99, but it's not going to tell you which one it is, okay? And then but M sub L obviously is directly related to L. So if you have an L value of 99, then you can have an M sub L value of any of the following. So -99 to 0, all the way to +99.
Okay. Okay, because I was kind of confused on 8 on like E. And then so L, it's telling you specifically like what it is. Like it's not like it's from what is it in -3 to 3?
Correct, yeah, so when L is 3, the only possible M sub L values are -L to +L, so -3 to 0 to 3, right?
Okay, because I saw that when n equals 5, I thought it would be from 0 to like 0 to 4.
It could be, yes, so L could be 0 to 4. However, we select, like they specified that it's on L equals 3.
Okay, got it. Thank you.
Yep.
Right, and that is time. So what did you all get for your answer? Still working? All right, raise your hand if y'all have an answer. I with pride.
Higher with pride. What is this? You're like going at a 45 degree.
Oh, sorry. I mean, straight up.
All right, a few more seconds.
Oh, yeah, that is me.
How did you get the job there? Was it through a health career?
Technically, I'm still there. I'm like a ghost member now.
Um,
Yeah. Mhm. Yeah.
Frequency, I can max out the energy. So if you have the frequency.
This is receptor, so it's singular.
You do that, you know, the equation E is equal to.
Our Rod's the ones for writing this note, though.
Mu or.
So are we using this one, right?
Yeah, exactly.
All I know is what.
So you could have gone a longer way and found the wavelength. Oh, wait. is that- here's the-
Yeah.
Oh, no.
So and if you do that, it's H times C over the wavelength.
Is it plastic?
H times C over lambda would be H times C over the wavelength, not
The answer is in joules, right? 'Cause you have the energy.
joules. As long as you converted your 750 to terahertz to hertz. Yeah, and then energy would be joules, yeah. Does that make sense though? Because when you derive the
Yeah,
equation,
you're right.
E is equal to HC over lambda, E is equal to HC over frequency. So your mouse looks like a transformer,
I've got a transformer, beetle.
definitely not a beetle. All right, are we ready to continue on?
Yes, that's because I got.
All right.
All right, so now would you get?
What did you give Maria?
I got the wrong answer.
Just,
Mine's just
say your
really
number.
weird.
It's very small. It's 4.96 times 10 to the negative 19
4.96 times 10 to the negative.
joules.
I mean, I'd say this is a pretty average one. Still.
Yeah, it's not small whatsoever.
2.6.
Pretty big, actually.
2.6. That's pretty massive, actually. 2.6. Okay, so we have those answers. Now let's go through this. So in general, a human eye cannot detect photons of frequency greater than 750 terahertz. That's not true. Don't look that up. Find the maximum energy of a photon that can still simulate the receptors in the eye. So first of all, what's the equation?
Energy of a photon is equal to Planck's constant times frequency.
H times F. Expands over F.
We're gonna do F just because it makes more sense.
Yeah, F for frequency. E equals HF. So what do we have? Right? We have the frequency, 750 terahertz. But do we want to use terahertz in the equation? Why not?
That's not the right unit. We need hertz.
Exactly. So let's do a quick conversion. So 750 terahertz. Now, how many terahertz are in 1 hertz?
10 to the 12.
Yeah, so one
10
time,
to the 12 hertz, 1 terahertz.
yeah, exactly. 1 terahertz on bottom, and then 1 times 10 to the 12 hertz on top. Because you need the terahertz at the end of the day to cancel out. So then if you solve that out, you'll get something along the line. So it's 7.5 times 10 to the 14 hertz. Now, right, we can go ahead and plug this into this equation. So let's do this. E, that's what we were solving for. This is H Planck's constant, which is 6.626 times 10 to the negative 34. And then, right, we have our other answer, which is my problem. That's 7.5 times 10 to the 14 hertz. So now, if we multiply those two numbers together, what do you get?
Well, we tried that. 96. There's no rounding there.
No, I don't like rounding.
Well, then I guess you would.
Is it over and it's a
If you use 3 sig figs, but doesn't that not matter anymore?
It doesn't.
yeah, that's what you said.
It doesn't matter. But you gotta round still.
Dr. Alvin didn't on one of his questions today, so I don't grab it anymore.
Okay. Interesting.
15.
I'm excited. Okay. What did you can just do it for them.
All right, so when we multiply it out, we get an answer of 4.97 times 10 to the negative 19. So yeah, this is the correct answer. So, yeah, whoever did this, Maria, you got it right. 4.96 times 10 to the negative 19. So, as a bonus question, what is the name of the receptors?
Is it for brightness, or are you talking about like color?
I mean, I was gonna go with rods and cones, but yeah.
Oh, okay, never mind, rods and,
Can't forget about cones.
yeah.
It's always rods, never the cones. All right, so anyways, yeah, this is, the way you do this problem is just a simple like unit conversion from your terahertz to hertz. And then you just go ahead and plug into your equation, then solve for what you're looking for.
Yeah.
That's like what a majority of this chapter is. Like chapter 7, just find what you're looking for, plug it into the equation, have a happy day. Pretty much all there is to it. So any questions about that? Does that make sense to everyone?
Thumbs up? Yeah, good, awesome.
When are you guys gonna post the key
Okay.
for this? Because I forgot to write it down.
I can just give you the answer.
Really? Can I take a picture?
All right, now time for number 10. Sponsor problem.
All right,
No, sorry.
we'll give you let's see, 5 minutes on number 10. Because this one's a bit of a doozy.
Yeah, that weird one. Is it Schrodinger or whoever? Schrodinger.
Hopefully it's on.
Let's not look at our notes either.
What? No, you
Kidding, I'm just kidding.
It's in paper now.
So ready for the weekend. Sleep in until 7 a.m. tomorrow.
Oh, that must be fun for you.
Look forward to my 7 a.m. sleeping.
Not a day this week, though. That's not a day.
Just not Thursday or Friday today. Okay. Let myself sleep in.
Sleep is important. Like me personally, I go to sleep at like 10:30.
He also prioritizes sleep on Saturdays, which is why your take-home assignments don't ever get graded.
And all I'm saying is the ones that Dr. Armand has sent us the keys for are graded.
That's true, that's true. All right. There's still time on the clock, but I'm gonna give you the equation we should be using here. So that way, if you are stuck, you don't stay stuck, or maybe you'll still stay stuck, but maybe this will help. This is known as what? Why did I say?
Rydberg.
Yeah, the root. It's open.
I know.
So the Rydberg equation. If you are still stuck, maybe you should think about your hydrogen emission spectrum series. So like you have Lyman series.
I don't think I have that much.
Palmer,
Oh my god.
That's actually chunky. You're such a.
Ash.
Okay, so how do you?
Yeah, that's why I said, oh, see, that's why I said, I was like,
Interesting.
which, yeah. Wait, what we trying to find?
The initial, yeah,
So
because
that
we know the
means-
final.
The final will have to be minor.
But y'all were thinking we forgot a piece of information in this column.
Yeah, I did.
Yeah, we did.
Maybe you forgot a piece of information in your lecture notes.
What do you mean?
Okay, if you still don't know, Frisch, what wavelength does a Lyman series emit photon in? Like what part of the ultra?
UV.
Yeah, what part of the
Electromagnetic.
electromagnetic spectrum?
Visible light.
Dude,
Balmer?
Is it Lyman?
Dude.
Oh, I thought you said Balmer. Lyman's ultraviolet.
And then what about Passion?
Ashton's infrared.
We're gonna review that IR, and this is visible. Yeah, Lyman and Balmer sound pretty close together. Now that I think about it. Okay, if you still don't know how to proceed with this problem, what is the final energy level that the electron lands in for a Lyman series? 1. What about Passion? 3. What about Balmer? 2. What? Textbook. There's series of the hydrogen emission spectrum. So like the Lyman series always emits a photon in the ultraviolet region, and it jumps from any energy level to n equals 1. So,
Oh, yeah. I'm good now.
so these are all things we learn from either going to lecture or reading our handy dandy textbook. All right. So it's asking for the initial energy level, which corresponds to which variable in our lovely equation, easy to use equation. At which Ni, right? So we need to solve for Ni. I could do this one of two ways, by plugging in the numbers and then solving for the variable, or solving for the variable and then plugging in the numbers. Which one would you all prefer? It's the only way to do it, right? Because you don't want to work with all those nasty numbers, right?
If you like math, you can work with the nasty numbers all you want. I mean, once you get to know them, they're not really that nasty.
Stop where you are, sir.
Some of us miss numbers, math.
So minus. We multiply by -1,
It's really easy.
so times -1. Yeah.
Do you have the early morning ones?
And final squared minus.
You are missing out. Let me tell you, I love numbers.
I'm pretty sure that we're actually at that.
Really? Doesn't matter.
I don't like using this equation. I'm just solving for Ni algebraically. So to solve for this, we would divide the entire left side by the same thing, and then multiply both sides by Ni squared. You would get Ni squared is equal to 1/(1 over n final squared minus 1/() wavelength times RH. And then to solve for Ni, you would get, you take the square root of all of this stuff. So you know what we're gonna do? Copy. Paste. Square root. Now we just have to plug in all the nasty, right? So clearly you would get Ni is equal to square root of 1/(2 squared minus 1/the wavelength, which we need to convert from nanometers to meters. So 433 nanometers. You know, in 1 meter, there's 1 times 10⁹ nanometers, which gives us a wavelength of what?
It's 10 to the negative 7.
4.3 times 10⁻⁷. Thank you. And we're gonna plug that part here. So 4.33 times 10⁻⁷. And we have to extend all this stuff. And then times the Rydberg constant, which is 1.1 times 10⁷ is 1.1 times 10⁷. And that's something we're gonna have to memorize. It may not always be given to you. And then close parentheses. And then if you plug all this into a handy dandy calculator, what number would you get?
5.
5 is the correct answer. All that work for a single digit number that we learned when we were like 2 years old. Unless you went to his middle elementary school when you learned it when you were like 3 months old.
Now you learned it straight out of the womb.
Oh, really?
Okay. Any questions? So the hardest thing about this problem, I'd say, is not recognizing that we have to use the Rydberg equation, because it's talking about the hydrogen emission spectrum. So obviously the Rydberg equation only is applied to the hydrogen atom. And it's also giving us info about energy levels, and it's asking us to calculate initial energy level. So the only equation that I think of when I am given this type of information, hydrogen emission spectrum and initial energy level, is the Rydberg equation. The hardest thing is probably realizing that you need to use outside knowledge to figure out what your end final is. It's saying that blue lines of the hydrogen emission spectrum, obviously that's going to be found in our visible light region, right? And we know that an emitted photon from in the visible light region comes from the Balmer series, which has an end final of 2. We have to know these 3 things and try to apply them. And we have to know that we have to apply them. And once you get that, the second hardest thing is just not messing up on the algebraic portion, right? Solving for the correct variable. No graphing calculators are allowed. I'm sure y'all are aware.
I got confiscated last exam.
Really?
Okay, any questions on this problem? Yes,
So there's another equation. When do we know when you're supposed to do that equation?
what the equation is?
The EN is equal to negative RH. And why is RH like different numbers?
Yeah, there's different Rydberg constants.
So we don't use that equation?
I don't ever solving problems using that equation. I think I know which one you're talking about. It's talking about the energy, right?
It's for the H, it's for hydrogen.
As well, yeah. Is there what? Let's see the.
I'm sorry, I'm making a really bad.
So in this case, you're only given like one n value. So how would you know to solve for, how would you be able to solve for a second n value?
Yeah, I know that. I just don't know when if we're gonna have to apply that.
Maybe eventually, it would just ask you.
Like it would give me,
It would say like, what is the energy of the photon being emitted?
so I wouldn't.
But I mean,
use-
you could, if you know that the photon has a wavelength of some thing, you can,
Yeah.
whatever, unless it doesn't give you that information. If you find problems like that online or something, you could always do them here. But if there's no questions on that, maybe we still got a couple more minutes, or do y'all want to end this session today or early, or you want me to find some more problems?
We should do the take-home assignment as no problem.
Oh, girl,
Yeah.
Yeah.
how about,
back
we-
of it.
how about we say we did, but we don't?
Oh,
Nice try, nice try. This is actually a very good problem set that I did myself when I was in your class. Rydberg equation. I would say. I'm gonna send this to y'all. Do y'all want me to send this to y'all?
Yes.
Yes, I'll send this to y'all. And then we will maybe. I mean, the key's on here. The key is down here. Somewhere. Yeah, here's the key. It has solutions. So you can. Do it at your own pace. I would say these are very good practical problems to understanding the concepts in this chapter. So I'll go ahead and erase everything and I will send you everything. Are y'all in the group meet? Y'all are, okay, I'm gonna send it into the group. meet. Okay. Is that a good deal? Do we have a deal?
Yes.
All right. I think these highlighted ones are ones that I wanted to make sure I did with the students last semester. So actually, I won't erase the highlights. But yeah, these are good problems. Okay? So please do them. It'll only help you. It'll take time. You'll get some wrong. You're bound to get some wrong. That's okay.
We're also bound to get some right, so.
Exactly. Okay, so what I'll do right now is share to. I'll share it after, but yeah, so. I guess that'll be the end of the session today. You want me to include this or send?
Include it.
Yeah, include it.
I'm gonna stop sharing my screen and I'm gonna send it to the group meeting before. And let me make sure there's no others. Oh, it's not a lot more practice problem. And there's a lot of stuff on there.
I had to figure out the way it should be.
Yeah, I mean, you can share it.
I think it's part of it.
Let me know if y'all get it. It just sent right now, so. It's a big file. If you have a wonderful iPad, you can just upload it to a new note, right? It'll be now.
Yeah, that's what I do all the time with documents. You guys documents on my iPad.
Exactly. Look at this.
So it's.
Waste of paper.
I am, oh,
Yeah, we know. I'm just kidding.
that's the sweet.
Don't worry about it. All right, so I sent it to the group meet. Is everyone in Zoom in the group meet? Perfect, Michelle, thank you. Awesome. If you're not in the group meet. Oh wait, let me make sure I get y'all's little attendance thing first before y'all leave. I'm sure some have already left. Let me make sure we track our favorite students. Make sure our favorite students
We're so honored. Thank you.
were. Okay, it's gonna pop up in like 5 seconds. There you go.
I already did it.
Pop up live.
I did. I'm serious. You can check.
Check right now.
I did. I did it.
How the QR code's not even up there.
Yeah, but I did it.
You want me to get it for you? Oh, wait, what kind of phone do you have? Oh, you gotta keep, oh, can you explain the Q4 of the take-home assignment? Maybe solve a similar problem. Which one was Q4?
Number two.
Two.
Okay, so If you saw what we did for question 10, the last question on take home assignment is similar to that. That's the only hint I'll give.
Okay, thank you.
Wait, which one? Question, I could totally open up the answer key on my iPad, but I don't want to.
Yes.
Well, you're recording.
We're not looking, we'll close our eyes. We'll close
Well,
our
I'm
eyes.
not
I'll take off my glasses. That's the best I'll give you.
Wait, which one was it, Rich?
Question 4.
Question 4.
The last one.
So last, which one we did?
Yeah, the last one, question 10.
What was question 4 though?
Question 4, it was the one with the.
Oh, the rubric one? Oh, yeah, it's the exact same thing, actually. No, not the exact same, it's a little bit more complicated.
Oh,
Oh, did you get the QR code?
Yeah, you wanna put up the group me thing, because my phone is working.
Yeah, actually, how about I do a little bit of.
It says statistics. I don't know. It's not even
Share
physics,
group.
so that is biology.
So someone needs a group meet now?
I thought it was like P values and stuff.
All right, that's the QR code for the, wait, I'm not even sharing.
As a function of time for an orbit cylinder.
So it's airstream.
I need to change it.
Okay, that's the QR code for the group meet. If you're not in it, if you are in it, then you should have got the thing for all the problems. And again, the answer key is at the end of all the problems. So, yeah, it'll be good. Do those problems, and I promise chapter 7 will make so much sense to you, okay? But do them on your own time. I don't think I'll cover them here, just because we're gonna move into chapter 8 and then pretty soon chapter 9 and 10 and 11. It'll go by pretty quick.
wait, that says 4 chapters?
So it's 7 or 11, yeah.
That's a lot.
Wait, isn't this like the last exam before final?
11's like not even that much though.
What is it? Lewis structures?
It's
It's molecular orbitals, right? 11 is.
molecular orbitals. You mean like the MO theory?
Yeah.
I don't think so.
First
You get that? Do you also need the QR code for
You leave
attendance?
out on like 6.
I scanned it.
You scanned it? Did it for you?
Yeah, we're done.
I need everything in on.
Couldn't go to lab.
We are.
Like research lab, yeah.
Oh, I need your
Are you
help
using
in
the-
my open.
No, it's not.
Oh, okay.
Chemistry student. Are you a leader?
Okay.
Actually,
I'm
have
driving.
you done this?
And Dylan a leader?
Both trying.
Dude, I literally, why did I think he was doing?
Often you guys have.
So I want-
I don't know anything.
Augie was saying that it was like, what in the?
Graphing calculus?
Can you help me on this one?